This is Tim Bryce with my column entitled 5 Easy Lessons for System Design. I never really understood the hubbub associated with system design. People tend to look upon it as a complicated process. Actually, it's not. Yet the corporate landscape is littered with disastrous system projects costing millions of dollars, all because developers overlook some rather simple principles for design and focused on technology instead. There are 5 easy lessons which can greatly expedite the development of any information system. To begin with, it's not a matter of following a rigorous set of instructions, but simply having a different perspective on information systems. To illustrate, number 1, information equals data plus processing. This is a simple formula involving two variables, data, representing the facts, and systems, how the data is to be processed. It also means there are differences between information and data. They are not synonymous. Data is nothing but the facts of the business. Information is the intelligence needed to support the actions and decisions of the business, and as such, it only has value at a particular point in time. Consequently, data is stored, information is produced. As an aside, there is little point in producing information if nobody is going to act on it. All system design projects begin with a definition of information requirements, not hardware-software specifications such as functionality. If the information requirements are improperly defined, everything that ensues will be incorrect and a colossal waste of time and money. Number 2, an information system is a product that can be engineered and manufactured like any other product. All information systems consist of a 4-level hierarchy where the product is represented in various levels of abstraction, from general to specific. This is no different than an architect designing a building or an automotive engineer designing a new car. This also means systems are designed top-down and tested and implemented bottom-up. When the various subassemblies are designed, they can be finished separately. This means a system design project can be conducted in parallel with different parts running concurrently. This is clearly a departure from the waterfall approach, which assumes systems are designed in a linear manner. The system structure consists of Level 1, the system, representing the product. Level 2 are subsystems, subassemblies represented by business processes used to collect data and produce information. And Level 3 is procedures, both manual and automated, interconnected to represent a flow of work. And finally, Level 4, either steps for performing manual procedures or programs for automated procedures. Number 3, systems communicate through data. Data is the glue holding systems together. It is the only way one part of the system communicates with another, through shared data. By identifying the individual data requirements for the subsystems at Level 2, we can then develop the business processes in parallel, knowing they will work together at the end of the project. Number 4, there are logical and physical dimensions to systems and data. Subsystems at Level 2 represent logical processing. It's what we want to do and when we want to do it. Levels 3 and 4 represent physically how the subsystem is to be implemented, which is normally based on economics and available technology. Whereas the logical portion of the system will rarely change, the physical portions will change more dynamically. For example, consider payroll systems used in business, both commercial packages and in-house developed systems. All provide the means to collect data regarding worker profiles, such as their salaries, hourly rates, deductions, and so on. Time worked, vacations taken, overtime, and so on. Producing the actual payroll and various government reporting tasks. How this is physically implemented, though, varies from one package or system to another. Yet they all satisfy the logical specifications. In other words, payroll systems have logically been performed the same way for many years. Their physical implementation, though, differs significantly. As another example, consider the various spreadsheets available, such as Microsoft's Excel, Lotus 123, Google, OpenOffice Calc. All fundamentally work the same, but are physically implemented differently under the hood. How a system is physically implemented is of little importance if it solves the problem effectively. Data also has logical and physical dimensions. A data element has only one logical definition, what it is meant to represent, but may be physically implemented many different ways. For example, consider the different ways time can be represented: dates, weights, money, and so on. Yet the logical definition remains the same. Logical data models of the facts and events of a business, such as customers, orders, products, shipments, and so on, are required for implementation in physical file management techniques, including database management systems. As should be obvious, whereas logical information resources will remain relatively static, the physical resources will change dynamically. And finally, number 5, documentation is a byproduct of the design process. Just like an architect or engineer who produces a set of blueprints depicting the various levels of abstraction in their product, systems developers should do likewise. At level 1 of the system hierarchy, information requirements are used to define the various subsystems. At level 2, the various subsystem definitions, complete with inputs, outputs, and logical files, are used to define the procedures. At level 3, the procedure definitions, including inputs, outputs, and physical files, define the steps for manual procedures and software specifications. At this point, level 4, there should be sufficient documentation for programmers to develop and test their programs. This approach is no different than an architect completing the blueprints before laborers can begin construction. In systems, programmers produce and test each program. They then test the software as a string at level 4, and test the workflow of the subsystem, including both manual and automated procedures, level 3. Then parallel testing of the subsystems, level 2, before putting the system into operation, level 1. Again, you design top-down, test, and implement bottom-up. The point is, good specifications can improve programmer productivity far better than any tool or technique. Yes, system design is actually quite that simple. However, people tend to make it more complicated than it needs to be. It's not a matter of lengthy instructions as embodied in methodology, it's a matter of perspective. If you can accept the concepts embodied by these 5 easy lessons, you can build any information system. That's right, any. For a free copy of my mini poster on information systems, see the Bryce's Laws section of my webpage at timbryce.com. Friends, keep the faith. This is Tim Bryce in Palm Harbor, Florida. Follow me on the internet at timbryce.com.